Welcome to the webinar for the OPC Machine Vision Companion Specification Part 1, and thank you for your participation. My name is Peter Waszkewitz, and I would like to thank Carsten Born for a lot of the content in these slides, especially the excellent robot example for the step model state machine. Machine vision systems cover an enormous range, as well for the types of systems as for their application. On the systems side, we have a broad range of form factors, performance characteristics, and interfaces for communication, but also for the user. On the application side, we often have highly specialized systems, each an individual piece of special machinery in itself. They require different configurations and yield highly diverse results, ranging from simple OK, not OK decisions through a long list of numbers to entire collections of images and 3D models. This leads to considerable engineering and deployment efforts. Here you see a timeline of the development of the OPC Machine Vision Companion Specification Part 1. It took us a little more than a year to get from the kickoff with the total working group to a release candidate, involving quite a few meetings of the core working group, as you can see in the detail view of this phase, and a lot more homework which you do not see. It took another year to smooth out all the kinks and reach the final version, and as you can see, the intensity of the work, if anything, did increase, not least because we brought into being the test implementation group. Its purpose is twofold: checking that what we had specified was actually implementable and usable, and creating a demonstrator to showcase the specification to the public, which we did for the first time on the SPS 2019, again about a year after starting the work. Who was and is behind this specification? The work was supervised and reported to a total working group of approximately 60 companies and carried out by 17 engineers from the data provider side, that is machine vision companies, and the data consumer side, that is other automation technology disciplines. Of course, not everyone can make it to every meeting, so we typically had somewhere between 6 and 12 people around the table, respectively on the screen, with a collective experience of about 150 to 200 years. Some words on organization. Standardization in machine vision is organized through the G3 agreement, originally concluded between the AIA, based in the USA, the European Machine Vision Association, and the Japan Industrial Imaging Association, later augmented by the VDMA and the China Machine Vision Industry Union. Its objective is to develop internationally accepted standards and avoid doubling and overlapping work. Twice yearly, technical experts meet in the International Vision Standards meeting for joint work and coordination in a schedule rotating between Asia, America, and Europe. Existing G3 standards include GENICAM, the EMVA 1288 standard for machine vision sensors and cameras, the GIG eVision, CoExpress, CameraLink, CameraLink HS, and USB 3 vision camera interface standards, VDI, VDE, VDMA 2632 Part 2 for the specification of machine vision systems, and now OPC Machine Vision. OPC Machine Vision is developed by a joint working group of VDMA and the OPC Foundation. VDMA coordinates and sponsors the specification under a mandate of the G3. The G3 and the OPC Foundation both provide acceptance of the standard. And now for the specification itself. We felt that before creating a model in the language of OPC UA, we needed a common understanding of what constitutes a vision system. And of course, we could not reasonably expect vision system vendors and their automation users to throw everything away and switch to OPC UA completely overnight. We had to build on existing systems, existing machine vision frameworks doing image acquisition and processing and communication with built-in or remote HMIs, PLCs via digital I/O or field bus, MESs via network. Interfaces which will also not go away all of a sudden, but will coexist with OPC UA at least for some time. Such machine vision frameworks typically have a result management, a configuration management, and a recipe management, as well as other resources which are not currently our scope. Our specification complements existing systems with a common abstraction. The core element of this abstraction is an external state machine, providing a standard interface to the functionality and the behavior of the system represented in the states of the state machine. In addition, there are methods defined to manage results, configurations, and recipes of the system. All clients, those shown here as well as additional ones, can use this abstraction to monitor and possibly control the machine vision system. Most of this functionality is optional in the specification to allow scaling to systems which may not have the resources or the necessity for this amount of flexibility. And finally, the OPC UA server can of course incorporate additional interfaces, for example other companion specifications like the AIM, when the system is also to be addressed as an automated ID device, or vendor-specific interfaces. We expect that subtyping of the CS interfaces will be very common. As we just said, our starting point is the actual machine vision system as it exists now. The behavior of the system is affected by an operator, as well as various non-OPC UA interfaces, for example traditional field bus interfaces to a PLC or direct hardware triggers to cameras and so on. What is frequently forgotten and was also sometimes difficult to keep in mind during our specification work is that the OPC UA server is not itself the vision system, but provides a somewhat abstracted view on the vision system. All OPC UA clients see the behavior of the vision system only through this view. And we also have to keep in mind that we are potentially in a multi-client setup and need to give all clients the opportunity to get timely insights into the vision system, not only that client, which may control the system at any given time. Behavior, as represented by the state machine, is only one aspect in our conceptual model of a machine vision system. There are also a lot of different types of data to be considered. We identified recipes, which describe the current job of the vision system. Recipes therefore typically depend on the product to be inspected and the task to be solved. And configurations, which describe aspects of the system itself. Configurations and recipes work together to ensure that individual instances of technically identical vision systems produce the same output for the same task on the same product. For example, the recipe for a length measurement may tell the system the locations and parameters to use for detecting the edges of the test piece. The configuration will typically contain calibration parameters, taking care of the inevitable variations between technically identical systems. Recipes and configurations can be input to the system as well as output, as they may be edited directly on the system and downloaded for backup purposes, or managed centrally and uploaded to various systems in a facility. The purpose of a machine vision system is of course to produce results from the image data they acquire and process. In addition, they also produce events and conditions, like error states and alarms, to inform clients about various occurrences. We believe that this concept is relatively generic for all kinds of systems, although the wording may differ. Due to the enormous variety in systems and applications, the actual data content of vision systems is very hard to generalize, except inside narrow application domains. Therefore, this version of the standard focuses on methods for the management of configuration, recipe, and result data, and on control and observation of system behavior. And thus, the fundamental core element of the specification is the state machine. But first, a few words on data management. We considered, and still consider, the task to standardize the actual contents of recipes and configurations over the vast variety of machine vision systems generally hopeless, as they range, like the vision systems itself, from the very simple to the highly complex. Also, they may constitute valuable intellectual property of the machine vision system vendors, which they might not want to put into the OPC UA server address space openly, in which case a black box representation is called for anyway. However, there is the need to manage recipes and configurations not only locally on the vision system, but also centrally, for example in an MES, and this requires appropriate metadata to identify and handle recipe and configuration data. These metadata have been modeled in the OPC machine vision specification, so it is possible to build generic management systems for recipe and configuration data without having to look into the contents themselves. Of course, vendors are free to add representations of recipe and configuration data to the address space of their OPC UA servers, but these will necessarily be vision system specific, usually even application specific, and thus proprietary and non-standardized. Much the same is true for results. They also may be simple, easily represented in the address space, or very complex and potentially also very large if images are to be included. They may be required on different timescales, in quasi-real time for control purposes, rather less urgently for quality statistics. It is typically necessary to be able to trace results back to individual test pieces and jobs, which requires appropriate metadata, and they can be quite dynamic at times, varying by recipe and possibly even by job. Again, therefore, the OPC machine vision specification standardizes a rich set of metadata to manage and trace results, not, however, the contents. So we can generalize our approach to the management of the various kinds of data in machine vision systems, and again we believe that this is quite a generic concept. First of all, data management is typically optional, to account for systems which do not have the capabilities or the necessity for this flexibility. Second, typically only metadata is standardized for representation in the address space, not content, as content will be frequently application-specific. Of course, in a narrow application domain, like code identification for example, result content could be standardized too. We always have GET methods to request lists of existing items according to filter criteria, and add-remove methods to manage the items. All transfer of actual content is handled through the standard OPC UA method of temporary file transfer. In the area of error handling, we have worked closely together with the robotics group. The specification uses standard OPC UA mechanisms like alarms and conditions, and follows the severity model of OPC UA Part 5. The model distinguishes between acknowledgement, indicating that an event has been received, which is typically done automatically by the OPC UA client, and confirmation, indicating that corrective action has been taken, which is typically done manually. Purely informative events may require neither. Conditions may, depending on their severity, require acknowledgement only, or acknowledgement and confirmation. Note that a system can exhibit several error conditions at the same time, and that the existence of an error condition does not necessarily mean that the system suspends normal operation. Suspending normal operation constitutes an error state in the state machine and occurs if corrective action is required to continue or resume normal operation. In this case, a condition to inform clients about the state is mandatory. As we will see in a moment, this occurs on the mandatory top-level state machine and is thus always the same, even in the case of vendor-specific operating modes. And this brings us to the centerpiece of the specification, the state machine, or rather state machines, because OPC machine vision is a collection of hierarchical state machines, which we will see in detail in a moment. The top-level vision state machine is mandatory, so that all standard-compliant vision systems behave identically in their basic operation. It has an optional vision automatic mode substate machine for the central use case of the specification, namely the automatic inline inspection system. Vendors can add additional modes of operation, like a manual configuration mode or a calibration mode, in a systematic way which is described in the specification. In addition, each state can have an optional vision step model substate machine to handle complex dynamic synchronization with external systems. You may notice that there are double transitions between almost all states. Transitions caused by an OPC UA method call are shown in black. Automatic transitions caused by the system itself in orange. Automatic transitions may occur, for example, due to a control input from another interface, reflecting the coexistence of traditional interfaces with OPC UA we mentioned in the conceptual model. Here we have the mandatory top-level vision state machine in more detail. It covers the basic steps of startup, operation, error handling, and shutdown of the vision system. The transition from the initial pre-operational state into the operational state is performed by the system either internally or due to an OPC UA method call. This is the point where future extensions to the standard or vendor-specific extensions would come into play. Currently, there is a select mode automatic method which leads into the optional but standardized vision automatic mode state machine. By defining other substate machines with specific entry methods, vendors can add proprietary operating modes. The select mode automatic method, or a decision by the vision system based on other input or internal circumstances, leads into the optional vision automatic mode state machine, which is a substate machine of the top level state operational, as indicated here. It provides a built-in standard automatic mode behavior. This handles the selection of recipes inducing transitions between the initialized state, which is the entry state under automatic mode, and the ready state, where the system is ready to execute a job. Executing a job in our model always requires the existence of a recipe. Note, however, that all these transitions may be automatic and that a system is not required to support different recipes at all. A simple system with a single hardwired task can go through all the states from startup and pre-operational through operational initialized into ready automatically and then signal itself to be ready to accept triggers for carrying out its single predefined task. Thus, the specification can be scaled down quite significantly. The model supports the notion of self-terminating jobs, which start upon some trigger, cause a transition into state single execution, carry out a defined task, and return to state ready after finishing that task. This corresponds to the typical situation of requiring one or several images of a single test piece, performing the evaluation, then return with a result. Note, however, that the state machine does not require the evaluation to be finished before the return to state ready. This state only indicates that the vision system is capable of accepting the next trigger. It may continue the previous evaluation in the background, yielding a result at some point in the future. Therefore, the availability of a result is not indicated by a state transition, but by an event, as it may be completely asynchronous. The model also supports the notion of continuously running jobs, which are also started upon some trigger, but run until explicitly terminated, yielding a stream of results in between. This corresponds to the typical situation of inspecting endless material, like textiles or sheet metal. Finally, the specification standardizes the vision step model state machine. This can optionally be used as a substate machine in any other state, most typically a single execution state, to model synchronization processes with the client. The step model dispenses with ing states, pass-through states like starting between ready and single execution. Instead, the model transitions immediately into the target state and, if need be, goes through a step model to give the client detailed synchronization information. The step model is optional in every state. It does not need to exist if such complexity is not required. Even if it exists, the system can decide to bypass it. In the entry state of the step model, the system decides whether under the prevailing conditions a synchronization is necessary at all. If not, it can go to the exit state immediately. If the system decides that synchronization is required, it transitions into the wait state instead, signaling this by an enter step sequence event to the client. Then, either by an internal decision, for example because of a signal on another interface, or due to the client calling the sync method, the system transitions into the step state in which it carries out some action. Then the system decides if more synchronization steps are required. If so, it transitions back to the wait state. If not, it leaves the step model state machine through the exit state. This means the number of steps can be changed dynamically due to prevailing circumstances in the system. We believe this concept to be very generic, but it is also somewhat complex. Therefore, we will illustrate it with an example. We assume that a vision system has to inspect two sides of an object using a camera mounted on a robot arm. The robot requires triggering to move to the inspection positions, and the vision system has to wait until the position is reached before taking its next image. The entire handshaking takes place in a step model state machine inside the single execution state of automatic mode. This means that the vision system gets a single job start signal, possibly with a part identification, transitions to single execution state, handles the entire synchronization with the robot there, and then returns to the ready state. Begin and state ready. The control system calls the start single job method, triggering the transition to state single execution. As this single execution state has the optional step model substate machine, it enters state entry of the step model. The vision system knows that application specific, it needs a step sequence to carry out this job. Therefore, it enters the wait state and fires an enter step sequence event, which is caught by the control system, whereupon it moves the robot into the first inspection position. When the robot is in position, the control system calls the sync method. The OPC UA server then transitions into the step state and triggers the vision system to carry out its task, namely the image acquisition. The vision system does so and signals completion to the OPC UA server, which then transitions back into wait state, firing a next step event which is caught by the control system. The control system then moves the robot into the other inspection position and again calls the sync method, causing the second image acquisition. The vision system knows, application specific, that the complete single job is now done. Therefore, the OPC UA server transitions into the exit state of the step model and fires a leave step sequence event. The control system catches this event and returns the robot to its initial position. Meanwhile, since this is a self-terminating job, the vision system has finished the job and the OPC UA server returns to the ready state, firing a corresponding event which is caught by the control system so that the entire cycle can start anew with the next part. Thank you for your attention, and we are looking forward to your questions.